Hello everyone. So today we are going to learn backtracking in grid related problems or graph related problems, I could say. Only one thing which you need to remember for this type of problems. Rest all things are similar to what we have learned in the previous videos for backtracking related to string related problems or backtracking related to subsequences, combination sum related problems. Okay. So the common thing to general algorithm follows the same thing. Okay. First, if base condition, push in answer or return true. Okay, based on the condition, push in answer and return or just return true, depends on your question. Okay, follows one single path and complete full graph. Okay, backtrack and try another sequence. I'll let you understand what I mean to say with these things. Okay, so we'll just understand it with two simple examples today, and I'll give you some other examples of graph related in the description which you can try. So we'll try to solve rat in maze, which is very famous problem of backtracking, and M coloring problem, which is actually asked in many good companies, which is also related to backtrack. So first let's see the rat in maze problem. Okay, the question is little bit lengthier, but we'll read and you will get it. Okay, so it was said that consider a rat placed at position 0, 0 in an n cross n square matrix maze. The rat's goal is to reach the destination at position n minus 1 cross n minus 1. The rat can move in four possible directions: up, down, left, and right. Now, the matrix contains two values. 0 means a blocked cell through which rat cannot travel, and 1 is a free cell through which rat can pass. Your task is to find all possible paths that rat can take to reach the destination starting from 0, 0 and ending at n minus 1 n minus 1 under the condition that the rat cannot revisit any cell along the same path. Furthermore, the rat can only move to adjacent cells that are within the bounds of matrix and are not blocked. If no path exists, return an empty list. I hope you got. Okay. So, with this simple example, if I could make you understand, let's say this is the matrix given to you. Let me give an example of matrix. Okay. So, let's say a 4 cross 4 matrix is given to you. Okay. And the values are 1000, 1101, 1000, 1101. Third is 1100 and 0111. Okay, so this is the positions are given. 0 means blocked cell. Initially rat is at 00 position. So what is your base condition in this case? That if your x is equal to n minus 1 and y is equal to n minus 1, and that means that you have reached the end position, that is the destination. So we will push back the path in our answer and we have to return all such possible paths. Okay, so this is the one path, this could be another path. Okay, and there could be some other paths also available. So all such paths we have to push back in our answer, and that should be in lexicographically smallest order. So let's say initially this goes down and then left and then up and then right and then again down left. Okay, so it should be in lexicographical order. I mean, down should be first, left, up, and right. Sorry, R and then U. Okay, so DLRU, this is the sequence that you should follow while going from the top position to the n minus 1 position and down, left, right, or up. Okay, so now what is the thing which you can, so this is the base condition. Now for this type of problems, every time, let's say this is the position 00, okay, and you go first down. Okay, down is possible to go because it is 1. Then with the down, now you have to, now this down is fixed. Now you have to try all possible paths from the down. I mean, again you go down. Okay, so down, down, and then this side is you go right, and then again you go down, and then right, and then right. So this is down, down, right, down, right, right. So this is one of the possible path which you explored. Now after you came here, you will backtrack this R. And from this point, you will see, is there any other position to go? I mean, down is not possible, left is also not possible. That's why we go for right. Now comes U. Is it possible to go U for up? No, not possible. We'll again remove this. Again, with this, we came down. Is it possible that rather than going to right, we can go up? Because after right, U only comes. And we have reached this R only if down and left are not possible from this D. Okay, down and left are not possible from this D. Right? So with this D, we went to R. With this D, we went to R. And from the second D also, rather than going down, we can go to R also. Not left, but we can go to R. So with this D, we can go R, and then D, and then R, and then R. So D, R, D, R, R. This is another possible path which you could explore. So initially, you have to follow this sequence. Okay, with the D, if you got, then okay, choose D and go down. Until the point you can go down, go down. Now with this point, you cannot go down, then try for left. Okay, you went to left. Okay, now there is a possibility of going to right also. Sorry, you can go left. There is a possibility of going in right also, but this we will explore while we backtrack this, while we pop out this. So that's what I've written as the second point. Follows one single path. I mean, you follow one single path after taking at one time, and then backtrack and see, is there any other path available from this point? Okay, not available, you will backtrack, see if there is any other path possible. Yes, possible, then explore now this path. I hope you got my point. And this way you will complete full graph and then backtrack and try another sequence. General backtracking algorithm only. This is how the difference is. Okay. Let's code it and you will get it in a better way, I could say. Okay. So let me share the screen. Fine. So the condition says that, okay, this is maze. First, let's have this maze dot size as our n. Okay. Now, if maze of 0 0 is 0, then we cannot go, so we will return empty array. Okay, we'll return empty array. Now we have one vector of string, because this is string answer. Oh sorry, vector of string answer and string path, I could say, which is nothing but empty as of now. Cool. Now you will start from 0 0. So we will have one solve function as of now. Let's make first that. So we'll have solve function. We have I, we have j, which are the initial positions. Okay. Now, what is the other thing? We could have one maze, and then we have vector of string answer and string path and int n also. Okay. So if I is equal to n minus 1 and j is equal to n minus 1, so this is your base condition. In this case, we will push back the path in our answer and we will return. Otherwise, we'll follow the sequence of D, L, R, and U. Okay. So now we have one int new x as, if we go for down position. Okay. You can convert this to by making a vector also, and then a for loop for traversing first down and then left. But as of now, for the simple convenience, I am writing it separately only. So we'll first go down. So new x could be x plus 1 and your new y could be y only, because that we won't increase. By going down, we increase x. Now what we do, if that is possible, so I'll make one function possible with the new x, new y, maze, and n. Now what does this check? This checks that the new x and new y's value should not be 0 and it should not be out of the bound of the array. This conditions it will check. Okay. So if it is possible, then we will go to the new x, new y and try to solve fully with the new x and new y. So this is I plus 1 and this is j itself. Okay. And then we have maze, answer, path, and n. Okay, but we have to push back d into our path as we are going down. Now this solve will try to solve it fully until the extent it can solve. If it cannot solve, it will return anyways. If this is out of bound, it will return, but it will try to solve. Okay, so if it tries to solve and it will get to the point after taking d, and then we will pop out this. Okay, now we'll do the same thing for left. So now my new x is nothing but, it's not I plus 1 now. New x is I only and new y is j minus 1, right? Same. If is possible, new x, new y, maze, and n, I will push back L into my path. This you can convert to a for loop for better optimized code. Okay. Solve will go for new x, new y, maze, answer, path, and n. And we will pop back the last value. Okay. Now we have new x as for right. For right case, our new x is simply I only and new y is j plus 1. Okay. And if that is possible, with the new x, new y, maze, answer, path, and n, I will solve it and then pop back it. And the same thing happens for up. So now my I is for up. If I'm going up, this is I minus 1 and this is j only. And this should be u. Okay, that's it. Now we have to make is possible also. So bull is possible, which takes I, j as new x, new y, and then maze and n. So if I greater than equal to n, or I less than 0, or j greater than equal to n, or j less than 0, or maze of ij equal to 0, in this case we will return false. So out of bound condition or maze is 0 means blocked area, that is not possible path, otherwise we will return true. Cool. We'll try solving this for 0 0, maze, answer, path, and n. Okay, and we will return answer. I hope you got my point. And as mentioned, we cannot visit it again, so we need to have one visited array also. So we'll have one visited array of n cross n size, which is initially 0. So every time we'll make this visited of ijs 1 under the is possible function also to check that this new x, new y should not be visited also, or visited of ij is equal to 1. Then we will return false. Okay, so with this we have done this. I hope you got. We'll solve another question and you will get a still better idea on what I'm trying to say. Okay, so let me paste the question here. So the question says that you are given an undirected graph consisting of v vertices and e edges represented by lists edges along with an integer m. Your task is to determine whether it is possible to color the graph using at most m different colors. You can use at most, at max, n different colors such that no two adjacent vertices share the same color. No two adjacent vertices. You have different m colors and two vertices two nodes should not share the same color. That is our condition. So you have to return true if the graph can be colored in that way or not. So same thing you have to do. Okay. Let's say any graph has been given to you. Let me draw the graph over here and we'll get the better understanding. Okay. So let's say this graph is given to you like 1 and then 2 and then 3 and then 4 and then again connected to 1. So this is an undirected graph and you will be given that m is equal to 2. Two colors at most you can use. So let's say I used color 0 and color 1. So this I colored with color 0 and then this I cannot color with 0. I can color it with 1. So now this possible sequence I have to complete, taking this is 0. This I cannot take 0, so I took 1. Okay, anything adjacent to 2 is there? No. So I'll come here, I'll follow the DFS normal. I'll come here with 3. The parents is 0, so I will make this color 1 because 0 again not possible for this. Okay, so I'll make it 1. For 4 also I cannot make it 0, so I have to make it 1 only. And this is the correct sequence. Okay, so I have to return true. Now here you do not have to return the total number of all the possible combinations. You just have to return whether it is possible or not. So for one condition also, if solve becomes true, that means by taking this first condition only it became true, and so I will return true. I'll not backtrack it, I'll not pop it out and check it for the another way, because with the same condition it is giving me true, so no need to pop it out and return another sequence. If it is given that I have to return all the sequences, then you need to pop out and check for the other sequence like we did in the earlier examples. Okay, so let's solve this. Okay, so I'll make the adjacency list of this vector of int adjacents of size consisting of v vertices and e edges represented by a list edges along with an integer m. So there are v vertices. Okay, so I have this v. Okay, now for int I is equal to 0, I less than edges dot size I plus plus adjacency of edges I0 dot pushback edges I1. I'm simply making adjacency list, and adjacence of edges I1 dot pushback edges I0. Now what we need to do, solve function with the ith node, the adjacency list. Okay, we'll also pass the color array, which is initially 0 for all the nodes. Okay, so for all v nodes it is 0. So and then once we color we will make it, so vector of int ampersand color, and what else we need to pass m different colors. Okay, so what I need to check, that I will color this, I'll go to, so if your this index is equal to n, we will return true. I mean you have colored all this nodes. Now we will start from c is equal to 1 to c less than equal to m. These are the different colors of coloring the ith node. Okay, so I will color the, so if is possible to color ith node with c color, we'll make one function to check if I can color the ith node with c color along with the adjacency list. If it is possible, I will color the ith node with c color. So color of I is c, and then we will check for solve of I plus 1 adjacency list color and m. Is that possible? If it is possible, we'll return true. Otherwise, I'll make this color of I as 0 again. I need to pop it out because this condition didn't made it possible. So if it is possible, it will return true. But if not, I need to pop it out. I need to backtrack it, and I have to try for another C color, another some color, next C++, whatever is the color. Okay. If for all possible sequence I didn't get return true from here, it will be for sure false only. So we'll try from 0th node, adjacency list, color, and M. Okay, and this will be direct return. So I hope you got. We'll take one possible sequence and then we will try for full sequence. Okay. We need to pass the n also, which is the total number of vertices. Okay, cool. Okay, so I'll post you. Oh, we have left to make the is possible. Is possible is just to check in the adjacency list whether any other node has same color or not. So bull is possible is int node int c, which is nothing but color, vector of int adjacency list, and we need to pass the color also. Okay, okay, we need to go for all the childs for auto ampersand child of adjacency node if color of child is equal to c. Okay, if color of child is equal to c, means that shouldn't be possible. Child should have different color. Will return false. Else we will return true. That's all. Okay. So I'll give you some more questions in the description to solve related to the graph, wherein we have to solve one sequence, and then if then continue for that particular sequence if possible. If not, backtrack and try for another sequence. Cool. Do like, share, and subscribe with your friends. In the next video, I could try to take some miscellaneous problems related to backtrack, and then we are done with the backtracking. Stay tuned, stay safe. Bye bye.